Hey, this is Tyler Monroe for the Standing Wave Project in Music 112 Section 1, Audio Electronics with Professor Riley. And to start off, I'm going to define some terms that have to do with standing waves. First off, we have standing waves. These are also referred to as room modes, and these occur when sound is reflected off of parallel surfaces, and then they cross back along their original paths. And then it causes phase differences, which cancel out certain frequencies, and then interferes with the room's amplitude response. This also causes increasing and or decreasing of volume levels at different frequencies around the room. We also have nodes. Nodes are points of no motion, and this occurs when a crest of a wave and a trough of a wave meet. We also have antinodes, which are points of maximum amplitude. That's when a crest and a crest meet, and a trough meet. Moving on. So why are standing waves unwanted in the recording and mixing environment? Simply because if the waves are traveling along their same paths, it does cause phase differences, which does cancel out certain frequencies, and then makes a song's response quieter. And what can we do to avoid creating them? There's these products called diffusers, which you put on the walls and stuff. Say my arm's a diffuser. If the wave comes and hits the diffuser, they're built so that the waves will bounce off at different angles, so that they will not cross back along their own original paths, and which will avoid causing phase differences. Okay, so to start off, I'm going to measure the parallel surfaces in this room, just from left to right wall, front to back wall, and then from floor to ceiling. So, got my tape measure. Go ahead and do that. First, we're going to do left to right. Okay. So the distance from left wall to the right wall is 14 feet. We're going to make it 3 significant figures and make it 14.0 feet. I'm going to go ahead and write that down. Okay. And then we have a front to back wall we're going to measure. And we're going to say that that is 9 feet 3 inches, which in decimal form will be 9.25 inches, or excuse me, feet, 9.25 feet. Okay. Now we've got floor to ceiling. And that's about 8 feet 8 inches, which in fraction form is 8 feet 2/3. And then we transfer that to decimal form. It's 8.66 feet, just for the sake of three significant figures. Okay. And now we're going to go through and find out how to find out the frequencies that would be canceled out or phased out in these certain wavelengths. So there's all my work for that. There's my numbers for that. The formula that we're going to be using, the original formula, is lambda equals V over F. Now what that means is lambda, right here, is a wavelength measured in feet. V stands for velocity, or the speed of sound. Or, not speed of sound, excuse me, speed of light, which is 1,130 feet per second at 68 degrees. It's not exactly 68 degrees in here, but we're going to assume that it is for our calculations. And then F stands for frequency measured in hertz, and that's what we're looking to find in the solution. But we can't find it like this, so we got to change the equation to frequency equals velocity over lambda. Who is it? Almost. Do you need in? Yeah, sorry about that. Give me in. And there's the new equation for that. Okay. So what we're going to do is I'm going to set this up for us with our with our numbers that we have at the top of my page. So we have left to right. And for the 1,130 feet per second, I'm going to put 1,030 or 1,130 feet or 30 point. So that's going to make speed of light 4 significant figures in our equation. 14. But since all our numbers are 3 significant figures anyway, it's going to be limited by that because it'll take the lowest number of significant figures when you do division. Okay. So I'm going to use my calculator, which I think are in the book bag. Alright, we have 1,130 divided by 14. I don't know if you'll be able to see it, but there's that. So because we're limited to 3 significant figures, I'm going to have it, and the answer's frequency is going to be 80.7 hertz. Then moving on. Speed of light divided by 9.25. And that's going to be equal, there's that. But we're limited to 3 significant figures once again, so we're going to make it 122 hertz. 122 hertz. And then our last one, which is floor to ceiling, in the order we went in was left to right, front to back, and then now we're doing floor to ceiling. And 1,130 divided by 8.66. Again, 3 significant figures. 0 is not a significant figure, but if I put the 4 in there, it would become 1, the 0.4. So we're going to make it 130 point hertz. And there's the frequencies. Thank you very much, and that's my standing wave project.